Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. All right. We're going to be doing something a little bit different here today, so it's going to be a chill. All right, here we go. I have a playlist, but we need to make sure that the audio is at the right level, so let's check this out. I feel like it's a little bit too low. Let's crank it up a little bit higher. Now it's a little bit too high. Let's go a little lower. Got to perfectly balance my voice and this music. Okay, I feel like that's a good level right there, right? Maybe just a smidge lower. Is it too loud for me to even... Okay. I think that's good. Actually, let me make it just a little bit less loud here. I can't even like hear myself think. Put that a little bit lower. This a little bit higher. Let's see what it sounds like. Okay. I think that's perfect. All right, let's see what the sound sounds like on X. Skeletal Ghost, how's it going, man? Sounds good. All right. It's gonna be a little coding stream, but I'm gonna... Well, actually, why don't we just introduce it here? All right, I think we're live on X, we're live on YouTube. Let's get started. Everybody, welcome to another Hoopo stream. We're doing a cozy vibes today. It's called Finetuning at Home, and I'm trying something new today. We're going to be putting music in the background. This track is called Finetuning at Home. It's a playlist, and it's all AI generated music on the Udio website. There's like a million different AI generated music websites, but this is kind of just the one that I ended up using. But a bunch of lo-fi, kind of chill out synthwave stuff. So hopefully it'll provide the perfect background vibe track for us to code. How's it going, Skeletal Ghost, Lil KM, and Sagar with the question, what is the GPU cluster? What is the VRAM? Well, we're fine-tuning at home, so we're really going to be using something way simpler than that. We're going to be using this. Watch-N 0.1 NVIDIA SMI. So every 0.1 seconds, we're basically going to call NVIDIA SMI this is the computer. It's a Ubuntu computer with a 3090, Ubuntu version 12. Can you fine tune using the Mac? Maybe one of the Mac Studios. So there's the Mac Studio. These things, you can maybe do it on that, but I don't know. It's gonna be hard. It's not. This isn't necessarily the use NVI top. Let's see this one. NVI top. I don't know about that. Doesn't exist. You can fine tune on a CPU if you really badly needed to do it, but it's just not going to be super fast. This 3090 is okay for what we're going to do, but it's because we're fine tuning smaller models. If we feel like we're not getting enough juice off this, we can try to fine tune on a bigger cloud machine, but we're trying to fine tune at home, so we're going to be chasing that vibe. Pip install NVI top. I'm not pip installing no NVI top. NVI top. Let's see this. This looks nice. Is this in the terminal, or does it do you open up a browser window for it? It's pretty good. I'll give it a star. How about that? Give it a little star. All right, so today we're going to be fine-tuning specifically a robotic foundation model called NVIDIA Groot. So NVIDIA Groot was released a while ago, but just 2 days ago, they pushed a bunch of updates to their GitHub repo that allow you to basically fine-tune their model. They're calling this N1.5. But that's what we're going to be trying out. So we have, this mainly makes use of the NVIDIA Groot repo and then also the Hugging Face Le Robot repo. So I have forks of both of these in which we're going to be fine-tuning on a dataset for a custom embodiment. So the embodiment that I'm using, I've shown it to you guys before, but it's this embodiment here. I call it Tatbot. It's a robot that does tattoos. I actually have a live cam here, so that's the live Tatbot cam. But it's different from the robots that they used in this, right? So the small VLA model, which is the model that we were using last week, talking about last week, that one is for these SO100 arms, right? And most of the data that they use to train the small VLA, it comes from those arms as well. I don't think that these ones right here. But the NVIDIA Groot is a little bit more similar to our embodiment because you can see here that actually it's been trained on a diverse set of embodiments, including bimanual dexterous hands. So our setup is bimanual. NVIDIA Groot 1 has a significant chunk of bimanual data in it, so therefore I feel like if we fine-tune this one, we're going to get probably a little bit of a better fit for our embodiment. So fine-tuning in this case is going to consist of, we don't really want to push too many gradients into the VLM or the vision encoder, text encoder, these DIT blocks. Like those are probably already at a pretty good state. What we really want to push gradients into is just these parts right here, this state encoder, action encoder, and the action decoder. And these are, as you can see here, they're noted as the embodiment specific modules, right? So these are the actual little tiny little chunks of neural net that are going to consume our actions and our robot state. And that's why you need to train them per embodiment, because this robot state is going to change depending on your embodiment, right? Even if it's the same dimensionality as the robot that this is designed for. I don't exactly know which one is the default embodiment for NVIDIA, but even if it's the same state, the joints are different, you know, they represent different things. So you're going to have to fine-tune these. And that's what we're going to be doing. So going Jamal and Majetti. All right, so first things first, we want to keep track of all of this, right? So I have a markdown file here within the Tatbot repo where I'm basically keeping all the relevant links that I need, right? The link to the blog, the link to the model, the link to the repo, so I can very easily open up those if I need them. And then I have the instructions starting all the way from cloning my repo all the way to actually running it, right? And I feel like maintaining these things is always very important because then 2 weeks from now, I'm going to completely forget what I did. So like this, I can just go and run it all. I don't like the audio. Yeah. I can't work with tracks that have lyrics to them. I need instrumental tracks only. Okay, so we're going to start this from scratch, right? So we're going to come here. Let's actually go into the home folder. Let's remove the current Isaac group that we have. So we're going to start from scratch. And then before we do anything, right, when you have forks like this that you're kind of working on, one thing that you always want to do before you start any work is basically pull from the main repo. So you can see here that in my fork, I'm 35 commits ahead of, but then 5 commits behind Hugging Face the Robot Man. What that means is that since I pulled and worked yesterday, the Hugging Face team has already kind of made some updates. So we can go there and click on that, and we can see what they changed here. So you can see they added dev container to the git ignore. They changed some citations here. None of these are super relevant here. They added another more documentation for the small VLA fine tuning. This is actually kind of interesting, right? Some constants. Let's actually add this one here. So this new thing that they added, small VLA.mdx. Let's put a link to that in our... Actually, we'll wait a second. We'll add it later. Let's pull first. Okay, so they added constants. Okay, some stuff here. Nothing that should really concern us. Sometimes you get merge conflicts, and that can be very dicey, but I think here, most of what they added should not impact the differences that we have in this code base. So we should be able to just sync forward, fork here, update branch. All right, so now we've updated the branch, and now you can see this branch is 36 commits ahead. So now we're clean. Now we're good to work for the rest of the day. We don't have to worry about stepping on any stuff here. So go in here, let's get pull those changes that we just did. What's it downloading? I wonder if they added some kind of assets here. We added HIL-SERL to the robot right now. What is HIL-SERL? HIL-SERL. Precise and dexterous robotic manipulation via human-in-the-loop reinforcement learning. Okay, so we got a nice little set of tasks here. They're using the Franca arms here, which is a pretty classic research setup. They got the dual arm setup. Nice. You got bimanual. 2 different grippers. This is kind of an interesting situation going on. You see here they got the kind of default gripper that comes with the robot, and then they got this other gripper here. This like black gripper. Right off the bat, this is a tricky task. You know, this is a deformable belt, you know, and manipulation with deformable objects is pretty difficult. Okay. So you have a reward classifier. You have a demonstrations. You have interventions. So interventions is kind of when you pause and then you pause some policy that's executing, and then you as the human take over and do the teleop for that. Okay, so basically Initially, we provide more frequent interventions to demonstrate ways of solving the task and prevent the robot from performing undesirable behavior. We gradually reduce the amount of interventions as the policy reaches higher success rate and faster cycle time. So this is actually like a whole like business model for robotics as well, right? So a lot of people who are trying to make robotics work in the real world, like one of the ways that they do that is they have this kind of idea of interventions, and they have this whole system of like robot teleoperators who can basically effectively SSH, but you know, not actually SSH. It's like it's a nice little GUI. They have the view, they can control the robot, and you have these people that basically go into the robot, and if the robot is ever in some kind of weird failure state, you have a human teleoperator that can kind of get them out of that. And then over time, the theory is that if you have a big enough robot fleet and you have enough of these robot teleoperators, that over time you can kind of use that as a way to kind of collect data, and then eventually you can train a policy that will effectively act as intelligently as the human or the human teleoperator. This is kind of like the ramped autonomy, if you want to think of it that way, where it's like you don't release robots that are 100% autonomous, you kind of release robots that are 50% autonomous, and then slowly over time you get it up to 99% autonomous, and then 99.9% autonomous, and then eventually you kind of only have a super small elite team of teleoperators that are extremely rarely teleoperating robots. So that's a strategy that people are using. So this is kind of on that theme. This is such a weird task. Jenga whipping? Who came up with this task? Why would you give a robot a whip and just have it whip things? That seems a little sketch. Okay. I don't know. Looks pretty cool though. But I guess that's what they added. All right, so let's go back to our root directory here, and let's start with the very first thing we're going to do here, which is just we're going to git clone. Boom. We should have probably put a depth equals 1 there. Let's do that. So sometimes with these repos, if you put the depth equals 1 like that, you don't have to, it goes a little faster. Let's actually see if it's any faster. So we're gonna delete that folder, and then we're gonna rerun this. A little bit faster maybe, but not that much faster. Okay. Then we're gonna use our favorite Python environment manager to set up a virtual environment, and the version 11, I got that from the README, so actually if we go to the NVIDIA GRUD here, we're gonna skip next. They do seem to use Python 3.10 and CUDA version 12.4. I think that's similar to what we're doing. I just don't like using older versions of Python. All right. Created the virtual environment, activated the virtual environment. You can see here, there's our virtual environment, and then we installed pip install .base, and this is going to pip install only really the stuff that we want. So you can see here they have a couple different, this is the kind of generic dependencies that you're always going to install, and then you have here the kind of optional dependencies. So .base installs only these ones here, right? So they have, for example, Orin here, which is interesting. The Orin is the same edge device that we have as well on Tapbot. So hopefully we can train on this 3090, and then we can deploy it to the Orin. That'd be pretty cool if we can train on the Orin, but it would be pretty slow. Oh my god, I hate vocals. I hate vocals, no. All right, we got some little house music. Let's remix. Oh no. Remix, but no instrumentals. Let's just delete this. Don't give me human voices. Remix. And let's do one that's a little bit more similar. Remix. All right, now let's try the one that we just made. Heat of the Night Remix V2. I just can't focus when there's vocals on it. There we go. That's a little bit more of my vibe. All right, so now we've installed the virtual environment. We need to take the data set, and for this, I'm just using this kind of like throwaway data set. Like, I'm not actually expecting this to like do anything useful. This is effectively just the TAT-bot. You can come here on the robot dataset viewer. It's just basically tracing out this pattern, which I call the calibration pattern. Here, I have what that looks like. This is what it looks like, right? So it's basically a circle, a squiggle, a horizontal line, and a vertical line. These are fake skins, by the way, so this is what I tattoo on. Okay. So it's really just a throwaway fine-tuning data set, but really the hard part is getting the pipeline to work, right? So getting this all to run cleanly. And then once it all runs cleanly, then we can collect a nicer, cleaner data set, and then we can just fine-tune on that. But today, if we can just get the whole thing to run cleanly, I think that we'll be happy with that, right? So we want to debug all the issues that are probably going to come up with this different state space, different action space. There's probably going to be keys that are incorrect. And then we're going to have to figure out a bunch of dependency stuff to even get it to train, and then a bunch of dependency stuff to even get it to eval. So that's the type of stuff that we're dealing with. But hey, that's kind of the reality of robotics, you know, like half of it is just dealing with dependency issues. Okay, so we're gonna export that as the dataset dir, and then we're gonna use the Hugging Face CLI to download that dataset. So let's come here, and there you go, downloaded the dataset. And this is the nice thing. So whenever you're debugging pipelines, you don't actually want to use your full fine-tuning dataset, right? Because the fine-tuning dataset's probably going to be a little bit bigger than this, right? So there's actually an advantage to using these kind of small bogus data sets, because this is only 4 episodes, so it's going to be very, very quick to download. One epoch is going to be very, very fast, right? If you're training on a cloud environment, it's going to be a fast download. It's not going to take up a lot of space. So having like one of these little tiny test data sets that is the same format that you're going to have for the actual fine-tuning data set, but is much smaller, I think is actually a cheat code. Okay. And then we're also going to have to copy this modality config file. So this is something that I had to create here. I put it in the config, and this is what it looks like so far. I don't think I have it 100% right, but you can see here, it's like this dictionary that effectively maps the robot style dataset into the Groot style dataset. So you can see, you're saying, okay, in the robot style dataset, the image on the wrist camera is called observation.images.wrist, right? But I guess in the Groot style dataset, you want that to be video, and then inside that, a dict called wrist, and then inside that, probably the actual observation. Here you have the indices, right? So the indices of the grip or the arm. I kind of just vibe coded this based on the examples that they have in the Groot repo. So if we actually go to the Groot repo, here in getting started examples, you can see, for example, they have the unit tree one. So this is for the unit tree. You can see the unit tree has hand, arm, wrist, or waist, leg. So that's the action space. Unit tree is the G1. You can do the whole body control, which means you're controlling all of the arms, all of the legs, the entire body at once, right? You're no longer separating it into kind of lower half of the body for locomotion and upper half of the body for manipulation. You're effectively using a VLA to do whole body control, which is, I think, how people do humanoids now, right? I think maybe we're beyond the separation of locomotion and manipulation, especially with, for example, the Figure 1X also does this. It's whole body control. So, question from Lil Kim. Are you going to participate in the Robot Hackathon this weekend? Kinda, but not really. I am kind of tracking it. I'm on the Discord. I'm trying to see what's going on, but I do have a family, so it's pretty hard for me to kind of just say, hey, I'm going to go hack for 10 hours on Saturday, you know, because I gotta take care of the kids. So Probably not going to actually submit anything or be part of a team, but, you know, I might just watch a stream, see what happens, follow it on the Discord. You know, I'm there spiritually. You can think of it that way. You know, I support the whole open source hackathon aesthetic. I think that's a great way to get people involved and a great way to push technical progress, but it's just hard to me to do because I'm a dad. Okay, so we see here the unit tree. This is the SO100, which is a little tiny arm. You can see this is what the modality JSON looks like. So I kind of made the Tapbot one kind of inspired on that, but I almost guarantee you there's stuff in here that's wrong, and that's kind of what we're going to be debugging today, right? We're going to be solving that issue. Okay, so let's copy from our Tapbot folder into the relevant dataset dir. And then let's run this load dataset. So I think this will just be an easy way to verify that our dataset is at least somewhat correct, right? So if something is wrong here, so right off the bat, right? So this is a little sketchy. What happened here? Skipping left arm as it's not found in both state and action dictionaries. Okay, that doesn't sound good, right? So either the robot has a left arm and the Groot was looking for it, or the Groot has a left arm and it wasn't in the robot. So let's very quickly go into the visualizer here and see if there is a left arm somewhere. So that doesn't actually seem to be the key or the case, right? If we look here, this is called left.joint0.pose. So in the robot style, the images are called observation.image.wrist, and then the joints are left.joint underscore, and then the number, and then .pose because it's a joint position. And you can see here it goes between basically, it's in radians, so -1.65 to 0.55, right? So why does it want left arm and right arm? Let's actually look at the unit tree one. Let's look at the SO100 one. Do those keys exist? State, single arm, action, single arm. State, left leg, left arm. So you can actually, I am kind of seeing this single arm, left leg, left arm. So I think maybe it wants it to be left arm. So instead of arm L, let's do left arm. And then let's do left hand. Let's do left hand. Left arm, left hand, right arm, right hand, left arm, left hand, right arm, right hand. Okay. Let's copy that. Slightly updated Tapbot config. And let's run this load dataset again. So we're hoping that it no longer complains about this. All right, there you go. You see? Okay, let's see state.leftarm.shape 64 by 6. So 64 is the number of steps. So whenever we ran this, we told it steps 64. So that's basically frames is the equivalent abstraction here in robot, right? Where each X amount of time you get a frame. So you can see the hand is moving slowly. So each frame is like a step. So 64 is kind of the batch dimension if you want to think of it this way. This is the actual dimensionality of the left arm, should be 6. The state and the action are the same. This is joint space control, so the 6.6 is correct, 6.6 is correct. Left hand is one-dimensional because we just have a little pincer gripper on this arm, so that seems correct as well. Okay, I think this seems good. Okay. All right. Preliminarily, it feels like we're okay. Let's go to the next thing we need to do. Okay, the next thing we need to do, and by the way, this list of stuff to do here, comes from this blog post here. So you can see that a bunch of the people from the NVIDIA team, so you can see here, NVIDIA. So this is like a bunch of people with NVIDIA affiliations. They created this blog post on Hugging Face talking about fine-tuning their model using a LaRobot dataset, which I feel like people aren't realizing this, but this is a big deal, right? Because imagine being at NVIDIA, right? You have so much money, you own kind of so much of the stack, right? You have the hardware, you're now getting into model training. You know, it'd be very easy to also create you have simulation, you know, Isaac Lab, all those things, Isaac Sim. It'd be very easy to say, hey, let's create our own kind of dataset tooling and dataset management software, right? Why would we use Hugging Face's LaRobot tooling, right? We'll just make our own version of that, which is kind of what they should do from a business perspective, but they decided not to do that. They're like, hey, okay, it seems like people like this LaRobot dataset format. They like the tooling that comes with it, right? I didn't have to write this visualized dataset tool. The fact that I use a LaRobot dataset format means that I just get this for free, right? And that's kind of the advantage of open source, is that you get a bunch of people working using the same kind of standard, and that allows for a lot of progress to be made for you, right? And the nice thing about LaRobot is it's also very easy to manage the datasets, download the datasets, right? You get all of that for free, but NVIDIA didn't have to do that. So I think it's a very interesting move that they decided to use that for this. They even published it on Hugging Face's blog rather than their own kind of blog page. So this is good for open source robotics. It means that we're starting to see kind of people accept the LaRobot dataset format and model management and all of that. And I think that's good, because it means that if you can get your robot and your embodiment working with this LaRobot format, then you're going to get a bunch of stuff for free, including this fine-tuning, which is effectively what we're doing. Okay. So the next thing we need to do here is actually run the training. So let's log into WANB. Oh, WANB login. Currently logged in as Hug. Okay, that's us. We need to export the WANB run ID and the project. So this is kind of annoying. So for example, in the when you're fine-tuning small VLA, the small VLA fine-tuning script, you can literally pipe in your WANB options as a command line argument. So you can see here, I can literally say, okay, use this project, right, when I run the script. But that's not the case for the Isaac Groot, the fine-tuning script, which I think is in scripts here. Yeah, Groot fine-tune. So they don't have that ability. They have the ability to report to WANB and versus TensorBoard. TensorBoard is kind of the more DIY. It's the way we used to do it before WANB. But that's the only option they have here, right? You can't actually specify the WANB project, which is kind of annoying. You have to specify it via environment variables like we're doing right here, right? Okay. So let's take this and let's run it. And there's a 100% chance this does not work. Never say never, but I can almost tell you it's not going to work. Okay. It's doing something. Oh, all right, here we go. Parsing error. Argument data config, invalid choice. Tapbot, choose from Fourier GR1, Unitree G1, SO100, single panda gripper, bimanual panda. Okay, so you can see what's happening here is that there needs to be a kind of a data set config, right? So there, beyond just this kind of mapping that we created with the modality file, we're probably also going to have to create a custom data class of some sort to deal with our embodiment, which isn't ideal, but it shouldn't be too hard. So let's go into this actual script and see what this data config is doing. So Control F, data config, data loader, data loading params, balance data set weights, data config class, and then you see how it's data config map. Okay, so this is all the arms. All right, and this is how we're going to add our thing. So let's add tapbot. Look at that, tapbot data config. Okay, and now we're gonna have to add the tapbot data config. Let's make this a little smaller, just to kind of get a vibe here. Okay, so it seems like basically they have each of these classes separated by these pound signs. And you can see that some of them are importing from bimanual Panda Gripper, some are not importing, inheriting, right? So whenever you see this, this means that this class object is a child of this class object. So it's kind of like, it's similar to that object. It has maybe some extra properties. And you can see this is what we really want, base data config. So there's a base data config up here. And this is an abstract class, which means it's not intended for you to actually create an instance of this. Really, this is just intended for you to inherit from. You can see cursor is eager. It wants to create it. It knows what to do. Okay, so let's start off. Let's use one of these as a template. Let's use a bimanual one. Let's use a bimanual Fourier G1 arms only. This seems like kind of a good starting point. Let's use this one. So we're gonna copy paste the Fourier arms only config, and then we're gonna go through it. And let's also copy paste this comment, just because, you know, I think the right way to think about code's style is to just adopt whatever people have, you know? So like I have my own kind of preferred code style and formatting and comments and stuff like that, but it's not always necessary to be super opinionated, right? So like if I'm here in the Isaac Groot repo, I'm just gonna follow the Isaac Groot standard. Okay, so let's rename this to tapbot data config. Tapbot data config. Video keys. This is going to be head, and then there's also going to be the wrist. I think that's the names, right? Let's reference our group modality JSON. Let's just put it up here on the second panel. Video.head and video.wrist. I think those should be the two ones right there. I don't know if there's order here, so actually let's look here. Let's just double check. If they're video head, hand left, hand right. Okay, sometimes the order matters. In this case, it might not necessarily matter, but it does seem that they have the head view first and then the hands. Head and then hands. Okay, so we should follow that same format. Let's do head and then the hands. Okay. State keys, left arm, left hand, right hand. That's what we have as well. Left arm, left hand, right hand. We have that as well. And then the annotation.human.action.task description. We don't have this action here. Ours is just called annotation human.task description. Let's see if the other ones are also like that. Get rid of that. Let's actually listen to some of our tunes that we created. Let's add to fine-tuning, add to fine-tuning, add to fine-tuning, add to fine-tuning. All right, so now, some nice little house. We're vibing right now. Oh no. No. Why did it use, I thought I told it to do instrumental. I'm okay with vocals as long as they're subtle. Like that one's kind of subtle, you know? All right, let's go back. We were looking here to see. Yeah, you see this? This is more similar to what we have. Annotation language instruction. Let's actually look at the SO101. That's the one that's going to be most similar to ours. or at least it's the code path that you know people have gone through the most, right? So annotation, human, task. Okay, perfect. That's exactly what ours is. Let's do that. Observation indices 0. What the hell does that mean? Action indices list range 16. Okay, I think the observation indices. Let's see if there's any. Are these all just the same? Control F. So I'm just going here to see if they're all the same. Okay, every single robot embodiment has that same value for that, so I'm gonna guess it's probably that, whatever it is, whatever that means. Action indices list range 16. There's actually only 14. So let's do that. Video modality, observation indices, modality keys, state modality, observation indices, state keys, action modality, language modality. What the hell is this? Observation indices. The return data will correspond to the original data at a sampled base index plus delta indices. Oh, okay. So you're basically offsetting the index, which is kind of what you're doing here, right? You're basically saying, hey, the robot data set has this specific dimensional vector, which is your input, right? Going back to the paper, this thing here, the robot state, right, has some specific order. So I guess if you had a robot where the order was kind of in a weird thing, you could... That's what this would allow you to do. It would allow you to kind of like mess with that order. Okay, transform video to tensor. Okay, so this is the video pipeline. So you can see here, this is what, whenever you're feeding this, you're going to be fine-tuning this, right? This image is going to get transformed before it can be fed into this vision encoder, right? So even just from a basic perspective, right, it needs to get turned into a data type that can be consumed by this, right? So you see at the very end, it's going to turn it into a NumPy. But before that, you see there's a couple interesting things here. There's video color jitter. This is a type of data set augmentation. So what this is going to do is, rather, especially if you have a small data set like this with just a couple episodes, you don't want to be feeding the same image every single time, right? You want to kind of have some amount of difference there, some variance. So this is going to change the brightness, the contrast, the saturation, and the hue just kind of ever so slightly in the video, so that whenever you're training for multiple epochs and you're feeding the same data over and over and over again, you're getting a little bit of a difference there. Resizes to 224 by 224, and then it crops it ever so slightly. This seems kind of unnecessary. Why would you crop it by 95%? All that's going to do is just cut out a little tiny bit of the edges. Huh. All right, whatever. For the state, you're going to turn it to a tensor, and then you're going to turn it into sine cos. Okay. It's kind of a weird... Do all of them have this? Let's go back up here. Yeah, not all of them have this. Okay, so I might not do that. Let's go to the, that was the Fourier G1 ARMS. Let's go to the SO100. So this one has the video crop, resize, jitter, NumPy. And this one just has state action to tensor and then state action transform. And then it normalizes it. Yeah, I kind of like this one a little bit better. So let's actually duplicate this. Can I duplicate this? I think I can do this here like this. Yeah. Okay, so now we're... Ooh. Data config. Let's go back down on this panel here. And then this is the SO100. So for some reason, the Fourier robot embodiment has this like weird like sine cos. I don't trust that. I'm just going to do this. Action, concat, and then Groot. Okay, so we're going to copy that. Okay. And we have it down here. So I think we're pretty much set here. That is, let's actually match this. How many spaces are there between here? So there's 2 spaces between them. Let's make it perfect. And then there's 2 spaces between the bottom one. Okay. So let's commit that. Isaac Groot, why is it not refresh? Come on, there you go. And for my git commit message, I'm just gonna put ASD. And this is something that I've kind of like I've been doing this a lot, and I feel like it's not good practice at all. So if you actually look at my commits, look at how many of these just have ASD, 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 ASD. And kind of what I was doing initially was I was using the kind of auto message. So you can basically do this and get an auto message. But I don't even read this anyways, you know. I don't read these auto messages anyways, and it introduces like a 1 second of lag because I have to click on this and then I have to wait for the inference and then I have to hit commit. So ASD, since my hands are already in that position on the keyboard, it's actually faster to ASD, right? And the whole point of git commit messages is that in a legacy software team, you would have a bunch of humans, so it'd be useful for humans to be able to understand each other's git commits and they would click on them. But the reality of our software engineering kind of in this AI future is that no one's ever going to read your git commits, right? If anybody's even reading them, it's going to be an AI, and if an AI is reading your git commits, they're just going to look at the entire commit, right? They're not going to necessarily look at that message. So that's kind of why I started doing this weird ASD. But I guess since I already clicked the button here, I'll just add it there. Commit sync changes. Okay, and then we're probably gonna have to pip install again, right? Because it's not gonna use the latest one, right? I'm pretty sure if we run this, it'll give us the same complaint even though we already updated it. Yeah, you see it's not actually there yet. So we need to basically reinstall. Why don't we go full Monty here and just literally delete it and rerun it? Yeah, let's do that. Let's go full crazy here. We're just gonna go back, delete, and then reclone. Oh. Shit, did I forget to push? If I forgot to push, that would be so upset. No, okay, we're good. I pushed it. Okay. That we already have. Let's retry this, just to double check. Let's make this a little bit bigger for you guys. If it's hard to see, just let me know. Okay, that's looking good. And now let's try the training. We should have solved that one error. Okay, let's see what the next error is. Okay, we actually got past that, so it was able to find our new data config class, which is good. So it's now downloading the NVIDIA group model, right? So you can see here it's in 4 pieces. It's safe tensors, which is a format that originated because you used to be able to basically put arbitrary code inside these files whenever you would load these weights, right? Like people could put malware in there, so then people came up with this safe tensors format that kind of prevents that a little bit. All right, using 1 GPU, tune vision backbone tower, false, tune backbone LLM, false, tune action head projector, true, tune action head DIT. So this is exactly what we want, right? So tune backbone vision tower, that's this thing here, right? Vision encoder. Tune backbone LLM, false, so that's this one here. So we're not pushing gradients into these. Tune action head projector, that's this thing here, action encoder. Tune action head DIT. So the head, right, this is the head of this is like, if you want to anthropomorphize a model, this is the ass and this is the head, right? So this is the feet or the bottom or the lower part of the model, and this is the head or the top part of the model, right? So the action DIT head is the head on the DIT. So this is the DIT, diffusion transformer, and then the head would be this thing here. So it seems like we're pushing gradients into the right things here. It doesn't say tune state projector, but I think that's probably in there. Okay. Video embodiment tag, new embodiment. Seems a little sketchy. Should there be a tatbot embodiment? I feel like we should probably have something called a tatbot embodiment, right? Little low rank adapter. That's probably a good way of fine tuning. This is how you did good old stable diffusion fine tuning back in the day, was with these LoRa's. You have a little bit of a warm up, a little bit kind of medium learning right there. Tune LLM, tune visual, tune projector. Okay, tune diffusion model. Ooh, this is kind of interesting. Okay, so we are actually pushing some gradients into this. Save every 1,000 steps with a batch size of 8. We can probably crank up this batch size, but I wasn't sure if we would get it yet. Okay. Let's see what else we can change here. So if we actually go into the fine tune, there should be some kind of fine tune config in here, right? Groot, data, experiment, scripts, Groot fine tune. All right, here's the actual data class for fine tuning. Dataset output dir. We probably don't want it to just go into the temp dir. Is that what we have it? Output dir. Okay, no, we have it correctly going into one of the tapbot directories. Max steps, save steps, tune LM, tune projector, resume, learning rate, weight decay, LoRa rank. If 0, no LoRa will be used. Conditional based on that. Let's see. If config LoRa greater than 0, config LoRa rank. Okay, so action head only. So maybe what's happening is that since we're using a completely new embodiment, we're probably we need to basically retrain these from scratch, the state encoder, action decoder. But maybe the reason they have this is because they are, even if they're using the same embodiment, right, maybe they have different tasks. So they have like a pick up an apple task, and then they have like a grab a motor task, right? And then maybe what they're using the LoRa fine tunes for is for like same embodiment, but different task. I don't know. That would be my guess. Bfloat 16, that's totally fine as well. Here's the training arg. Steps. 300 training epochs. So this is kind of what I'm saying right here, right? Where 300 training epochs means you're feeding this data set 300 times into the model. So the model is literally seeing the same episode 300 times. So that's why you have to put that image augmentation in there, because or else it would just start overfitting so hard to that, right? In fact, you probably want a little bit of like action augmentation as well, but that's not as theoretically sound, right? Because the image augmentation, the whole idea is like, okay, well, even if the image is slightly higher brightness, the action that you output should be the same, right? But that's not the same with the modifying the action, right? Supposedly, in the whole kind of core thesis of imitation learning is that the human is providing to you basically the God mode action, right? That like for this given input, observation and state, this is the action that you should output. So action kind of noise like that is generally, or action augmentation is not really a thing. State augmentation could be a thing. You know, you could take the state and kind of fuzz it a little bit. But okay. Right now we're just kind of waiting for this model to run. While we do that, why don't we actually open up a little NVIDIA SMI here. Let's deactivate. I don't want this tap pod. Okay. Control R and then watch. So the Control R is a very useful terminal command because it basically allows you to dig up older terminal. It's like searching over previous terminal commands. But you don't even need to do that anymore, right? Like you can just do Control K and then say watch NVIDIA, and there you go. Add follow-up every 0.1 seconds. See, you don't even need to know terminal commands anymore. The tools are just way better now, and they just know how to do it. Jesus Christ, this is still downloading. How am I going to waste more time? Okay. Well, one thing I can do is I can commit this. Let's just go back here. This is one thing that I still don't have figured out. I think, so for example, I have two different cursor workspaces open, and they're actually on two different computers. But one of the things that I run into all the time is that I'll make edits in one, and then it'll be annoying, and I'll have to kind of resolve some merge conflict with the other one when I pull. So people have tried to do this with work trees, Git work trees, right? Where if you have multiple coding agents or maybe multiple cursor instances kind of all committing to the same thing, you have work trees that allows it to be a little bit more clean. But that doesn't really seem like a long-term solution. So it's almost like the whole Git kind of workflow is kind of straining under this new paradigm of like agents working on the same code base, right? And even the Git workflow, you can, like, what is the most that it's been stress tested by, right? Like, if you think about, like, some super popular open source project, there's probably only on the order of, like, 100 people that are seriously kind of pulling and making changes and then pushing and then pulling and then making changes and pushing. But once we go into this kind of, like, agent world, we might get to the order of magnitude of like thousands of agents that are simultaneously working on something on a GitHub repo. So maybe we need to rethink Git, right? I know that's kind of a weird way to think about it, but what if you have a million agents all pulling and pushing on the same code base, right? Then you would definitely need something different, because by the time you pull, somebody else has already pushed, and then you're trying to fix a merge conflict that somebody else already pushed on top of. So it's going to get pretty crazy. All right, let's come here into our group modality. Let's replace it with this one. In here, let's save that. And let's Control Z on this. Or here, save. Then let's go to Git here. Let's undo that. Discard. We're going to discard the changes in that data config so we can push them on this computer here. ASD sync. Right, so now it's pushed, and now we're going to pull on this computer here. All right, pulled. I guess this makes it hard for me to see the ASD, you see, but I can always hover over it and I can see that this ASD is the one that was pushed at 9:59, which is the one that I just did. So, okay. Looks like we're almost done downloading this model. All right, here we go. No module flash attention. Okay, so dependency issues. So first thing we're gonna do is we're gonna just copy paste this, not into data config. Let's actually open up this here, this exact fine-tuning script. This one here, we're gonna give that to cursor, and then we're gonna give it this context here, add to chat. Let's see if cursor can solve it. And while it's doing that, let's copy paste flash attention. Let's go into the actual Isaac Groot here, and let's search in here. Equal to, so you can see here, flash attention to run pip install, force reinstall. We might have to do this. Let's see what cursor's trying to get us to do. Run NVCC version. You can install via pip. Yeah, so basically, we're probably gonna have to run this. I think this might be the... Which Docker file is this? So this is the Docker file, and you can see here 2 days ago for CUDA 12.4, right? PyTorch 2.6. So let's see if that's kind of on theme for us. Okay, so let's see what the version of PyTorch is here. Let's do Python import torch version 2.5.1 CUDA 12.4, 2.6.0 CUDA 12.4. It's not quite the same, but those are similar enough that I think we should be good. Let's also run this NVCC version just to see the exact CUDA 11. What the hell? Why is this telling me it's CUDA 11.5? That is a little sketchy. Maybe we use this Docker file. Let's try to just pip install this. If it doesn't work, then we'll do all this training inside a Docker file. That's usually the cleaner way to do it anyways. So let's do uv pip install flash attention. You can see, ooh, 2.41 post legacy build wheel. Okay, this is not looking good, guys. This is not looking good. So what we're gonna do is, they have a Docker file here, so let's try to use this Docker file. Okay, because I like that it's on the latest release, right? If this Docker file was older than the most recent N1.5, I would be a little sketched out. So let's actually try to use this. So we're gonna have to change our instructions. It's gonna be like this. So train, let's do train with Docker. So we're gonna have to docker build -f docker file -t. So -f is telling it what Docker file to use, and this Docker file is literally just called Docker file. Then we're going to have to give it a tag. So once it actually builds the image, what are we going to call that image? We're going to call it Groot train. And let's run that. So that might take a second. Okay, so you can see here it's downloading this Docker file, and these Docker files are out of control. It seems like every month these Docker files get bigger and bigger and bigger. Look at this. 3 gigs, 1 gig, 2 gigs. So much crap here. Okay, but while that's building that Docker file, we can kind of craft the Docker run command. So we're going to put this here. We're going to start from that. Docker run GPUs, RM removes it once we're done. We have to make sure that the Groot eval is Groot train. And then the command we're going to run is effectively this one here, right? But we also want to do some other things as well. So we also want to -v. We're going to want to mount the wherever this model is downloaded, right? So if you remember, the first thing this script did, this train script is it downloaded this Eagle2 and the pre-trained Groot. So if we don't mount wherever this was downloaded, then it's going to re-download it every time, right? So then basically every time you run this Docker container, it's going to try to re-download it. So I'm pretty sure this downloads it in the Hugging Face cache location. We're also going to need to mount this here. So our dataset dir. So we're going to mount that, and we're going to, let's just say -dataset, and then we're going to be able to say -dataset here. So we can actually say dataset dir dataset. Okay. And they always change the Hugging Face cache dir, like they keep changing the name of it. So let's open up a new one. Let's check. Deactivate. Okay. HF, I think it's called cache. No. Echo Hugging Face cache location. Hugging Face home, I think that's what it's called. There you go. Okay, mount SSD1 Hugging Face. Okay. Mount SSD1 Hugging Face. All right, there you can see the robot. Calibration. Okay, so that's the data set. Modules. Transformer modules. Oh, there it is. You see Eagle HG model. So that's totally it right there. Okay. So let's take that. We're going to have to say mount this Hugging Face home, and then where do we think the Hugging Face home directory is going to be in this Docker file? Well, we can look for it, right? Let's see. Control F, HF, home. Okay, so what's going to happen is that when we run this Python script in here, it's going to search for the Hugging Face home directory and search to see if the model's been downloaded in there. When it tries to do that, it's going to use the default Hugging Face home directory, and the default Hugging Face home directory is going to be set here whenever it tries to load it. So let's go here into the scripts. Groot Finetune, and then at some point it's going to load the pre-trained model. Maybe here when it loads the dataset. Video backend dataset path. Okay, so this one just takes a pure dataset path. Path, dataset path. Okay, that seems fine. Let's go beyond that. Where does it load the model? Here we go. Groot N15 from pre-trained, and here's the base model path. So where's the base model path? Base model path, NVIDIA Groot N1. So that's kind of like a Hugging Face path. So actually, you know what we can do? We can probably... Where does this script download and download the pre-trained model to? We're vibing. How's the music going, guys, huh? I feel like it's been pretty good. It's not even playing the playlist anymore. It's kind of like auto-playing something, but seems to be mostly working. Pre-trained model weights are downloaded to your Hugging Face cache directory by default. Fine-tuned model checkpoints and outputs are saved to output dir. Typically under this cache Hugging Face. Okay. Let's see if that... Okay, that doesn't exist on our specific computer, but that's because... Oh. This is still downloading. This Docker file is going to take the entire stream to build. Watch it take the entire stream. Okay, close out of this one. So, we're going to assume it's that. .cache dash Hugging Face. Oh no, oh no. We gotta skip the skip. Okay, so this mostly seems right. We're also gonna have to mount this output dir. Okay, so that it outputs in that output dir. So let's also mount -v. And we're going to say output. And then here, we're going to tell the Docker container to write it out to this output file here. We're also going to need to add the wandb variables here. And this one as well. Okay. I don't know if you can add, I think you might have to wrap this in quotes, so let's double check this. Let's do, can you, is this Docker command formatted correctly? Let's get it to do it for us. Should be no spaces around the colon in the volume mounts. Okay. The entry point command should be part of the same Docker run, not a separate line. Okay. Okay. There we go. Go back up to the top. All right, so now we have our little Docker command all ready to go. Now we just need to wait for this Docker file to build so we can test it out. I guess what we can do while we're waiting for this to build is we can SSH into the ORAN and then try to debug the evaluation on that. Okay. Close out of this. So, what we're gonna do here This is our training computer, and this is going to be our eval computer. So actually, let's come here. Let's push the commits that we have on this computer. You can see how we changed that. Come back here, pull. Okay, that one should be good. And then here, we're now going to connect to host. We're going to connect to a different host here. I think 9.6. I want to say 9.6 is the Orin. One second, I gotta... All right. Connected to remote. Minimize that. Can't open display, that's fine. We're gonna go into tapbot, we're gonna git pull. Okay, then we're gonna control P, and we're gonna open up the tapbot. Jesus Christ, come on. What's going on here? Let's open this folder, actually. It's annoying, we're gonna have to log in like 4 separate times, but that's just the way it goes, guys. Okay, so you can actually see here, this opened up all the crap we were doing with the robot. But let's actually delete that. So let's remove .rf larobot. And let's clone actually both of those. So we're gonna git clone our Isaac Groot. Let's also put the depth one in there. That's what we should have done. Okay. Oh no, wait up, Z, Control Z, Control Z. Don't save. See, this is what I'm talking about. It gets really sketchy really quick. Because you have a lot of different computers on slightly different commits, and if you kind of don't track it very quickly, you could quickly end up in a sticky situation. So let's actually exit out of this one here. We don't want to be in that one anymore. We only want 2 open. We want our training computer, which is currently downloading this Docker container, and then we want the inference computer, which is going to be this one here. Okay, so on the inference computer, we're gonna have to modify. Where's the tapbot? We're just vibing. Just chill Friday vibes. Okay. We're gonna have to build the Docker file on the Orin computer, so let's do that. We're gonna call it Groot eval. Let's make it big for you guys. So unfortunately, we're gonna have to sit through another long Docker build here, but you can see what we're doing for this one. Let's close out of these. Is we're now 2 separate Docker containers. This Docker container is going to be the one that we train in, right? You can see this is a starting, so this is like the original Docker container. This is a CUDA 12 PyTorch 2.6. But for the inference, or the eval, we're going to be using this Orin Docker file, which starts from this L4T Jetpack, which is basically the kind of edge compute Docker container family for the NVIDIA Orens and Jetsons and those kind of things. And you can see it's kind of similar. Most of the dependencies are already here, right? So you don't really have to change that much, right? It's just adding a couple things, adding some Python, copies the Pi project, and then downloads or installs with the pip install.oren, which only pip installs the Oren dependencies in this Pi project here, right? Which are a little bit different. So right off the bat, you can see here, the base image is using Torch 2.5. The Oren is using Torch 2.7. Okay. Both of these are downloading. How are people doing? Do people have any questions? Questions about anything. Doesn't even need to be related to this fine-tuning. So this is the Wanby project. There's probably a couple failed runs on here. No, no failed runs yet. Okay, we're good. What is the end goal for my fine-tuning here? So the end goal is to get this Groot N1 on my specific embodiment. So Groot N1 is, or this is N1.5, which is the kind of latest release that was just a couple days ago. And they had released Groot N1 like months ago, but they only just recently added the fine-tuning scripts. Right, so you can see here 2 days ago. So that's kind of what I'm working on. But Groot is trained on these embodiments. So you can see here you have the Fourier, you have the Unitree, you have the Panda, and then you have the SO101. Right, I don't actually know if that's the 101 or the 100. But these are the embodiments that the Groot has been trained on. This is my embodiment. So this is TapBot, right? Here, I can show you guys TapBot. This is the robot cam for TapBot right there. So TapBot has different state space, different action space than these embodiments, right? So we're gonna have to fine tune the state encoder, action decoder, and I think it's also pushing gradients into this diffusion model here as well, the action expert, it's sometimes called. So this would be the vision language model, and this would be the A in VLA, vision language action. This is the action expert. So yeah, once I fine tune it with my embodiment specific data, which is this, right? We should be able to see how general it is, right? So technically I could go in there and I could just type in like pick up Apple and see what the arm does. So that's probably not going to work, right? Because this isn't a very good fine-tuning data set. So why is this not a very good fine-tuning data set? Well, one, it's only 4 episodes. You can actually literally see my child in the back there while I was recording this. But I think ideally something more on the order of like 50, maybe even 100 episodes would be better for a fine-tuning data set that gets you to go to a different embodiment. But also, I probably want a little bit more general, right? So this embodiment data set is pretty much, or this fine-tuning data set is like exclusively this like tattoo calibration task. I probably want to collect a fine-tuning data set for my robot that has a variety of different tasks in it, right? Like maybe picking up a block, putting something in a cup, right? So that there's a little bit more variety in this text here, right? Because whenever we're going to be fine-tuning, so far every single one of these episodes has the same exact text that's going in here, right? And the vision is almost exactly the same as well, right? So if we really want to take this generalist foundation robotics model and really get it to work well on our new embodiment, we probably want a bunch of variety in this, right? So that's kind of the next step here, is that once we debug this fine-tuning workflow, which is really what we're doing today, is just kind of dealing with dependency issues, Docker containers, just getting everything to run, right? And you don't need an actual good data set to do that. You just need like an example data set, right? Just get it to the point where you're training something, and then you can take the checkpoint from the training and run it on your edge device, and then actually get the policy to perform inference, right? If you debug all of that, then all you have to do is go back, re-record an actual data set, and then fine-tune on that. But yeah, we want more variety with this, right? So I'm gonna have to figure out how to get like a nice little representative data set of our tapbot embodiment doing a couple different things. Dude, this is, I think it's because I'm streaming. That's why it's downloading so slowly. This finished downloading, so you can see it finished downloading. Now it's just building. But part of the build is to download pip stuff, so. Root uses the Eagle 2 vision language model. Eagle 2 is fine-tuned from small LM2. So it's actually all Hugging Face. See what other data sets people have on here. Sort by recently updated. So 10 days ago, someone created SVLA SO100 sorting. I think this is small VLA with the SO100 robot and then sorting. We can copy it and then put it in the dataset visualizer. The robot visualizer. Put in that dataset. Let's see what this one is. So you can see this one has 50 episodes. A little bit more than that. Observation images top, observation images wrist. Shoulder pan, shoulder lift, elbow flex, wrist roll. So they named each of the joints here. Right? You can just see how like fuzzy these are. Action, observation.state. Okay, so actually the observation is the dotted line, and then the action is the red line, which are pretty much right on top of each other because it's all in joint space. Right? Theoretically, you don't need to do that, right? You can imagine a situation where your state is like different from your action, like your state is in like Cartesian or something like that, but I don't know why you would ever do that. Okay, this is still building, and that's still building. Okay, let's actually figure out how we're going to run this policy. So kind of the same way that we built the Docker run command for training, we have to policy with Docker file. So it's going to be very similar to this, but we need to figure out what we're actually going to run. Inference service. I think this is what we want. So let's actually go on to here, and then we'll type inference service. Right? We're looking for an example command. Here we go. 5, policy deployment. Run the following command to start the policy server, right? And this is also an important point that even though we're doing the inference on this AGX Orin here, right? Which has 30 gigs unified memory, this is not actually going to be controlling the robot. We're going to have a different computer called the Meerkat, which is just a CPU computer that has the actual cameras plugged in. That's going to be the one that actually controls the robot. This one is just going to act as a policy server. So it's basically just going to host the policy inside a Docker container so that whenever the robot computer says, hey, here's an observation, give me an action, this thing is giving it the action. Okay. Model path is the path to the checkpoint. Okay. And then inference policy is the script. So let's come here. And we're gonna have to give it the output folder. So you see how this thing here is going to, the training is going to put it into this folder, but that folder is not on the right computer. So we're gonna actually have to transfer the policy from our computer into this computer. So before we can even do this, we're gonna have to say copy pre-trained or policy checkpoint into OHO, which is this Orin. I think, I name all my computers weird names like that. And this is going to be here. And where are we gonna put this? Well, we're gonna put this into home OHO tapbot. Actually, let's not do that. Let's just do temp. We're gonna put it just in a little temp folder here. And that means that whenever we're running our policy, we're gonna have to mount this. So -v, we're gonna mount that specific folder. Let's call it checkpoint. And then the model path is going to be in there. So inside the Docker container, this is gonna be the path it's going to, so that's where we're gonna point it to. Get rid of this. Data config, this one's also gonna have to change. Oh shit. This is an issue, right? Because this Docker file is not going to be using our branch. See, this is gonna be an issue. Because this Docker file is gonna use the actual Oh no, it should. Okay. Yeah, okay, this will be fine. Sometimes these Docker files, they pull the repos, but this one is actually using whatever local repo you run the build from, so that should be fine. Okay. I don't like this embodiment tag new embodiment. That, I feel like, to me that just screams like it should be, we should have our own embodiment there. Let's actually look at this. Let's understand what is going on with this embodiment tag here. Search for new embodiment. Okay, all the examples have new embodiments, so maybe it's not as sketch as I think it is. Okay. Let's go back to this, and you can see that this is going to be the policy server, and then the client node is going to be inference policy. So you have inference service and then inference policy. Is that what's happening in this one here? Getting started examples eval robot. Getting started examples eval robot. External robot inference client. Yep, that's the same one. And then you have to provide it the host. Host port. Okay. So this is where we're gonna have to give it the location of our OHO there. Let's try something that it moves slightly upwards. Right. Give it something that is probably gonna work even though our fine-tuning data set is kind of trash. Oh, this one finished, guys. All right, our training. Oh no, this is not the training. This is the eval. Okay, the evals also. Do we need this? Hey Hupo, I have a question I couldn't find the answer on the internet. If anyone on the chat can answer, any metric to measure the overfitting on a model? Yeah. That's a classic, here. Here you go. This is like almost a classic question that they ask in lots of machine learning interviews, but let's say you have this situation, right? Where you have your loss on your training data set and then your loss on your validation data set, right? So your validation data set is basically a subset of your data set that you never actually train on, right? So when you have your original data set, let's say this one here, just to use our example, right? Maybe you only train on episode 1, 2, and 3, and then you validate on episode 0, right? So initially, as you train your model, your loss is going to go down, right? Your model gets better at effectively producing the right output given a certain input, right? And you start giving it more epochs, which means you're feeding the same data in over and over and over again. So the model is just going to start effectively kind of memorizing, given this input, produce that output. And that's what overfitting really means, is that your model is just kind of memorizing and fitting too strongly to the data that it's being trained on, right? So the loss curve for training is always going to go down like this. But at some point, you're going to start seeing the validation loss kind of go up. And what that means is that now your model is getting better and better and better at the training subset at the cost of actually losing generality and losing the ability to actually perform well on this validation data set. So whenever you start seeing that divergence like that, that's when you know you're overfitting, right? Is whenever you're like, okay, it's still getting better and better at the training, but it's like starting to get shittier at the other thing, right? Here's another graphical description of training loss with varying learning rates, underfitting, overfitting. And it's also like, this is kind of a continuous thing, right? It's not like a overfit, underfit is not like a binary. There's not just like some arbitrary threshold. It's kind of like a continuous thing, right? So like, it's almost like baking something in the oven. You can be like kind of overfit, kind of underfit. And sometimes you want this type of stuff, right? Like, where's a situation where overfitting is like what you want? Well, imagine a scenario where I'm going to deploy this robot in an extremely constrained environment, and it starts overfitting to the data set from that very constrained environment, and it starts getting worse at these kind of more general purpose tasks, right? It's like you're getting it better and better at like putting this ball in this cup, but it starts getting worse and worse at picking this hair gel. But you know that in your specific business use case, you don't give a shit about the hair gel or the performance on this. You only care about this. So there is situations in which you actually kind of almost want to overfit a little bit, because you know that your model is going to be used for this very specific thing and that very specific thing only. But I think as we move into kind of the more modern world where you have one model kind of doing more things, right? So that was more the case when you had kind of more specialist, kind of narrow AI. But I feel like now that we're using things like foundation models that are basically expected to do a variety of things, right? Like these models are taking in text like this because they're expected to have some general ability, right? It's like you're giving it this text because you want the same model to be able to pick up an apple and pick up a pear. You're not going to have an apple model and then a pear model. You're just going to have one model that kind of does both. So yeah, I would say overfitting is probably less good now, but that was kind of one random scenario that I came up with where you could overfit and it's fine. Okay, so we're going to test out the eval that we just did here, but 100% it's not going to work because this checkpoint isn't even a real thing. But I want to see if it fails on the checkpoint not found or whether it fails on some other thing. So let's test that out. Invalid flags, RM and GPUs. Oh, I think it's GPUs all, like that. Failed to create task, OCI runtime. Bro. Bro. First of all, let's fix this. This is GPUs all. I think we can just do GPU 0 because it's just one GPU. Question from Cole. I want to 3D print some robotics. What do you think is the best open source robotic kit to start with? The SO101? Yeah, 100%. I think it's just, like, the answer to that question actually changed over the course of this week, right? If you were asking me that question on Monday before this came out, I would have said, yeah, the SO101 is probably a good idea. But now that NVIDIA is also releasing their open source foundation models and fine-tuning using the SO101 as the kind of like cornerstone kind of embodiment, I feel like it's even more of a good idea to use the SO101, right? the more people that buy into this kind of LaRobot kind of story of like, hey, we're going to be using LaRobot style data sets and we're going to be using this specific SO101 embodiment, the more advantageous it is for you to use that as well, right? So if NVIDIA was going to use mostly their humanoid, then the SO101 is less useful. But now that you have NVIDIA also kind of supporting that, and you have LaRobot supporting that, and I actually saw the ManiSkill. You guys know this is a pretty good simulation framework, but I recently saw the SO101 in here as well. So now that everybody's kind of adopting the SO101, that I think it's a no-brainer. It's the best idea. Any metric to say this model at any epoch has 5% of overfitting instead of extracting features from training data? Overfitting is like, it's hard to have like a specific, precise, like quantitative definition of overfit. Like 5% overfit, that doesn't make any sense to me, right? It's like, you can give specific examples. So you can say, hey, here at this specific point, here's one specific data point where given this input, it produced this output, and then given this input, it produced this output. And then you can make an argument for overfitting at a, like, it's kind of too generic. It's like a high level generic term, not like an extremely precise term where you can say this is like 10% overfit. Okay, we were... is after the... So, correct command, okay. Can't open file dash workspace dash scripts. No such file or directory. Okay, so basically what's happening here is that we're trying to run this scripts inference service, but that doesn't exist exactly there. So what we're going to do is we're going to do this. We're going to get rid of this Python, and we're just going to say bash. And that will just put us in the Docker container. So now we're in the Docker container. We can hit ls. There's nothing there. If we do Python, import, let's see. From Groot eval service, if we do import Groot, no module named Groot. Okay, that's not good. Import LaRobot. No module named LaRobot. Uh-oh. Uh-oh. Okay, so the problem here is that this Orin Docker file, it's copying over the Py project and it's installing this pip3. So actually we probably need to do Python 3. Let's do this. Python 3, import Groot, import LaRobot. So first let's do which Python 3 and then which Python. Okay, they're kind of the same. Sometimes those can be different. So I think we might have to modify this Docker container here. We basically wanted to copy all of the scripts as well. Right, we wanted to copy Groot. Ideally, you would have a Docker ignore that basically says don't copy over all this other shit, but copy over the relevant stuff. So we're gonna have to do this. Let's come into Isaac Groot. Let's go into the... Actually, let's try this. Let's see if we can get it to do it just with mounting. We're gonna get out of this Docker container, right? And you can actually, because we put that --rm flag, you can see we're not running any Docker containers here. So we're gonna do the same thing. We're gonna try to go into this, but we're gonna -v, and we're gonna say home, ho, Isaac, Groot. Groot has like the most annoying name. I don't know who thought about putting the double zeros in there. It's so annoying. And we're gonna put that in workspace. Isaac Groot. Okay, so now we've mounted that in there. Oh my god, it's the same bullshit. What was the fix to it before? I think you gotta put this in here. You gotta get rid of this like this. Oh, Jesus. Fix me, help me. Help me, cursor. Must come before the image name. Ah, okay, that's what we're doing wrong. So you see this image name here, Groot eval, needs to be before. So it needs to be right here. Okay, so now inside our workspace, you can see we've copied over the Isaac Groot directory. So now we're kind of in our Isaac Groot folder inside kind of the Orin itself, which is now being mounted as a volume into the Docker container. So now if we do pip3 install like this, most of these should already be installed, so it'll be totally fine. Okay. Now, let's run the Python script here. See, so now it knows where the script is because we're basically putting it in from our previous thing, so. This should fail on the no checkpoint found. At some point it should basically be like, I don't know where the fuck this checkpoint is. Yeah, unrecognized model in blah, 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 blah. Okay. So let's actually take this and put it in here. So we're gonna say bash-c, I think it is. And you say that and this. So now when we actually go into this, let's exit out of this. We're gonna have to put this in there. We're gonna have to mount this, just like we did. So now we're mounting the checkpoint folder, and we're also mounting the entire Isaac Groot workspace into the workspace. Then rather than just immediately running this Python, we're gonna first install Orin, which will basically overwrite what's already on there. So you can see that's what happened here. Installing Groot. Oh, already installed it. But that's the one that it installed from the Pi project, which is the older one. Or not the older one, but the one that's not our fork. And we wanted to install our fork because our fork is the one that has the tapbot data class. So that's what we're doing here. Okay. This is probably, there's probably like double quotes or something that I'm missing here. Let's actually run it, make sure it works. All right, so there you go. Went in. Pip installs. Now it's going to try to run the script. There you go, running the script. Unable to register cuDNN. Is this a warning or is this an error? Warning, warning. Just like generic CUDA errors. This is like, you know how there's like studies in like hospitals where, because in a hospital there's always those like beeping sounds in the background, like the nurses and doctors just like learn to ignore the beeping and then the beeping has no use anymore. I feel like these kind of like warnings are the same thing with programmers. It's like there's just always like 700 different warnings here that I just have learned to just ignore them, and it's probably not a good thing that I ignore them. All right. Fuck. I'm almost out of time here. Let's see where we are with these other ones. Ooh, all right. We finished the training. Let's actually see if we can get the training one to work at least. Okay. So we're there. We want this one. We're probably gonna have to do the same thing, so let's do that actually as well. Well, actually first let's confirm. So if we go into this Docker file, does this one copy over the entire workspace? Ooh, this is actually a little bit sketchy. Okay, no, here you go. So this is exactly what we want. You see that? It copies over the scripts, which is what we want, so that's good. Okay, let's run it. This is gonna have to be GPU 0. No module Groot. Okay, same problem, guys. Same problem. Let's run the bash in here. Yeah. Why would you give me a Docker container where the scripts don't even fucking work? You know, like what the hell is that? This one's going to be a little bit trickier because you see how right here, when you copy this and you run the pip install, then there's this crap right here, right? So if we mount the stuff here and then pip install again, it's going to get fucked up. So we basically need to run this after mounting the entire folder. Okay, so we're gonna basically do something similar to what we did with the other one, except, so we're gonna mount in this case it's gonna be -home -oop -Isaac Groot. That kind of rhymes. That's very pleasing. -home -oop -Isaac Groot. Into workspace, right? Then here, now we're gonna have to say bash-c because we're gonna run a couple different things. First thing we're gonna do is we're gonna pip install -e, but we're gonna do no deps. I think we also want it to, it's more complicated than this because we want it to only, let's see what this looks like. Let's run this. Exit out, clear. Okay. And there we go. Ooh. Oh, this is no bueno. You see, we're we're going to control C out of this, is trying to download the model again. So what that tells me is that it didn't, it tried to download the model, which means it didn't find it in this cache folder, which means whenever it went and it said, okay, I'm going to run this model, it tried to find it, it couldn't find it, and then it tried to re-download it. But we don't want to have to re-download it every single time we run this Docker container, right? So we have to figure out where the cache dir is. So here's what we're going to do. We're going to delete all of this. So we're just going to run the Docker container without the command, right? Which is going to put us into the Docker container. Bash. Now we're in the Docker container. Now, if we import transformers dot, there's like some kind of like cache dir. Here, let's see if the terminal knows this. Find the transformers Hugging Face cache. There's probably some function that'll print it out. Okay, here we go. Of course. Doc cache dir should be in user's home dir. Yeah, if we ls... Oh, there it is. The problem is there's no Hugging Face cache in here. Oh, it's dash root dash cache. Maybe that's what's going on here. If we do dash root dash cache, maybe that's what we want. Let's first see if there's a command. Let's use GPT-3. Let's use 4.0. Let's give it the same problem we gave this one here. How can I find what the HF cache dir is inside this Docker container? Maybe we can just set it. Okay, here we go. HF Hugging Face Hub, import Hugging Face Hub download. Okay, so let's do Python. Oh. And then let's do print. Oh my god. I don't want this path. Why did it give me this path? The Python path module is trash. Oh my god. All right. Let's do this one here. Okay, that's totally it. You guys were right. Dash V was pointing to, it needs to be dash root dot cache Hugging Face Hub. Okay, so now we're going to say our Hugging Face home. We're going to point it to that. Okay, let's get out of the Docker container. Now let's rerun this. Let's actually run it like this. Okay. Quick build overwrites the Groot. That's totally fine. Going on there. Found no NVIDIA drive. Okay, that's good. That's good though, because it basically means that it found the downloaded model. Now it's trying to actually run this. Couldn't find. Let's see. If we just run this, but without all this crap here. Let's see if we can verify that the GPU is actually working. Okay, so now we're in the Docker container with the Hugging Face cache. Let's do Python. Let's do import torch. Let's do torch.cuda.isAvailable. If I can spell available. Is that how you spell available? Why does that look wrong? False. Uh-oh. What the hell? I mean, that is a CUDA 12. Maybe we need to force reinstall Torch. Fuck, that is not good. NVIDIA SMI command not found. NVCC. Okay, that's correct. There is CUDA on here. Let's try to run this. It's not good, guys. The Docker container that they gave us doesn't have CUDA on it, or doesn't have NVIDIA. Maybe whenever I did this pip install -e no deps, maybe it didn't install, it like overwrote what was already on there. Dependencies are fun. Come on. Install that torch. Okay. Jesus. All right. We're going to copy this. And we're going to Control-Shift-I. We're going to give it this. We're going to say, does the Isaac, or does the Groot Docker container not have NVIDIA? Question mark. We're going to give it the Docker file. This one. And we're also going to give it the Groot Finetune script. Let's see. The container itself is CUDA capable, but the absence of NVIDIA suggests that NVIDIA Container Toolkit is not being used. You must start the container with the GPUs all. Is that the problem? Dude, if that's the problem, that would be hilarious. That was it, guys. Holy crap. I almost had a heart attack there. Alright, so the only issue there was that I had GPU 0. For some reason, I guess I was confused. Usually when you specify devices, you can do that, but --GPUs all is what you want to do. That was almost, that could have been bad, guys. That could have been sketch as hell if the Docker container had no NVIDIA. Okay. Running. Oh, loaded the model. Loading checkpoint. It's tuning, guys. Oh, fuck, we need a Wanby login. Fuck. Go to your API key. So we go to the browser. Where did that open? Open. I think the way they present this, they don't show you the whole key, so I shouldn't. They only show you the front of the key, so I should be fine. I can show this. Oh. Come on. Come on, weights and biases. All right, there we go. Copy. Control-Shift paste. Enter. There we go, guys. No space left on device. But we did successfully create, there should be one failed run in here. There it is. Look at it. This run is called dash output. That doesn't seem right. Run ID should be Groot test. Fuck kind of output dir dash out. Come on. Oh no, here it is. Groot test. There it is. Why is it called dash output though? That's terrible. Okay. Let's copy paste this into cursor. Why does this Docker container not have enough room? Let's actually verify df-h. We should have. There's a bunch of space on this device, so I don't know what it's talking about. Docker system prune af -- volumes. I think this is what we want. Shim size. 32 gigabytes. It's a lot. Let's do 8 gigabytes. Okay. Now let's try. And this should have also created here inside our tatbot calib folder. It should have created tatbot, output, train, tatbot calib test, Groot. There you go. This is going to be kind of annoying if I have to keep logging into WANB every single time. Okay, interesting. Unexpected input output. Torch size 8, 14, 32. So the 8 is this batch size. The 14 is the action shape. And 32 is probably the length. So what's probably happening here is that I think our dataset doesn't have enough steps. So we probably need to take this 32 and tune it down, right? Because this is basically doing action chunks, and I think it's probably not. That's my guess, is that it needs more chunks. It needs longer chunks, sorry. So let's go into the Groot fine tune. or specifically here, model Groot N1 line 126. Models Groot N1 line 126. Okay. Let's control F in here. Let's say 32. So where is that 32 being set? Let's see if we can find it here. Search for 32. So at some point, here's the LoRa. That's not what we want though. Max action dim. Is that it? Batch size 32, no. Max num embodiments 32, no. Depth 32, no. Float 32, probably not. Length 328, no. Okay, nothing obvious. We need to figure out what that is. Groot N1, line 183. I think it's Control G, 183. Validate inputs. This should be handled internally, however, we'll need to do this after the deadline. Okay. Good to know. Action.shape should be 3. Action shape 1 is action horizon, and then action shape 2 is action dim. So action horizon is what we want. So let's search for action horizon. 16. We want the action horizon in training. Length of action indices. So you see, if not type OK, then it prints out the action type. So you see here, it didn't print out the action type. What it printed out was the shape. So if not shape OK, prints out the action shape. Okay, so since we are loading this, let's do a PDB right here. And because we're doing this mounted thing, as soon as I modified this file here, that's the actual file that's going to run when I run this Docker container. So let's do that. Okay, now we're in the Docker container, and now we're going to run this. And when I run this, it'll run it, and it should trigger on this debug trace right here. So first it's going to ask me to log into Wannabe, but for this one I'm actually going to say no. Don't visualize my results 3. Okay, it's going to run, boom, triggers it. Now we're inside this Groot N1 file right before it fails. And let's see what the action.shape is. So this is the 8.14.32. So it is 3, which is fine. Let's see what self.action horizon is. 16, and then self.action dim. 32. Okay, so actually, the action dim is correct. It's the action horizon here, which is 14, and it should be 16. Okay, so at some point, we're setting action horizon to 14 when it should be 16, or 14 when it should be 16. So my suspicion is that this has to be the file that we made. So where's that file? Groot data dataset, this one? Where was that file that we changed? Data config, here it is. Okay. Action indices list range 16. Ah, that's got to be it, guys. Here it is. Action indices list range 14. Let's change that to 16. Okay. Now we can get rid of this. Or actually, we can just actually, because it's literally already there, we don't need to do anything. All we got to do is just pip install again, and then we can run it again. Why is this not? Okay, let's run it again. It'll still trigger in that breakpoint, but now we should see action shape 1 correctly be 16 instead of the 14 that it was. Okay, now we're there. So now action.shape1 is 16 and self.action horizon is also 16. So this should now work. Out of memory. Okay, so that works. Let's get rid of this import PDB. And let's try a batch size of 2, because that is something. So I was training the small VLA on this computer, and it was pretty good at a batch size of 64, but you do have to remember that the small VLA model is significantly smaller than this. Yeah, like look at the Groot is about 3 B params, and the small VLA is way smaller than that. It's like 400 M or something like that. I guess why can't I see the size of it? I used to be able to see the size of it. Here it is. Model tree, preview not found. All right, either way, it's smaller, right? So let's make the batch size smaller. Okay. Batch size 2. Let's run it. While that's working, let's Control-Shift-G. We're gonna add those. We're also gonna there should be a change on this one. There we go. Out of memory error again. Oh no, guys. Are we literally gonna have to batch size 1? That's no good. That means that we're not gonna be able to train this on this 3090 if we're using a batch size of 1. So what we're probably gonna have to do is rent a cloud machine to do this. Yeah, okay. Thanks, Rupinder Singh. I appreciate that support. I have no words in which I can thank you enough. Hopefully this is useful, you know. I don't know. I realize that these coding streams, like I say this every single time, but they're just not as popular as like the paper streams. I figured maybe adding the music would make them a little bit more enjoyable to listen to, but yeah, they're not as fun as paper streams. They're not as information dense. You know, a lot of it's just kind of me just debugging random bullshit, which is not as cool. But you know, I think it's just part of the experience. I think for some people this is useful, right? For some people that maybe are just getting started in machine learning and coding and programming, it's like they don't really know, like they want to know, what does it actually look like for someone to do this, right? Because I think with any kind of human skill, it's like you can read a textbook, but really what you want to do is like watch someone do it, right? Just like if you can look at someone do something and you're like, oh, okay, so that's what it is, right? So if I'm quote unquote programming or like doing machine learning, like what does that consist of? Well, it consists of this. You're just kind of like keeping track of the commands you're putting in. You're just kind of like fiddling with these little commands. Like that's what it is kind of day to day. So, you know, hopefully this is useful in that sense where it's like people can kind of get an idea of what the vibe is, you know? And this is how I spend most of my days. You know, I just sit here, I have some music in the background, and then I just kind of fiddle with this stuff. All right, I'm like way over. This should have been done 30 minutes ago, so I'm gonna call this a success, even though we literally ended it on an out of memory error. But the next step here would be to have to open up a cloud machine and then run it on the cloud machine, and then there's gonna be all the cloud machine stuff that, whatever, I'll deal with that later. But anyways, guys, I appreciate everybody hanging out. Hope you guys have a good weekend. Thank you, Ed, Rupinder, Snooks, Mark, Jamal, Cole, Richard, Radane, Oraz, Lil KM, Sagar, Josh, Majetti, Sheldon. Thanks everybody for hanging out. Have a good weekend, and see you guys later.